Roads play a significant role as part of essential and basic social infrastructure for livelihoods and economic activity. Coupled with other environmental improvements, road infrastructure has invigorated economic activities and dramatically enhanced people's daily lives. As part of JICA's aim to build foundations that improve user safety and amenity and support economic activities in developing countries, it has supported numerous road developments, including main road repairs, grade separation at intersections, and bridge construction and replacement. Road pavement consisting of an asphalt mixture or concrete slabs not only distributes and transmits weight of vehicles as heavy as 50 tons to the soft ground, but also allows for smooth and safe driving on a flat surface. To achieve these objectives, asphalt pavement consists of a surface course and binder course made of an asphalt mixture, and below that, a base course and a sub-base course. It is the subgrade that supports these pavement layers. Road design in Japan defines the subgrade as being up to a depth of 1 meter below the pavement. Similarly, concrete pavement consists of a cement concrete slab and a base course overlaying a subgrade. Road pavements, which support the heavy traffic of today, are damaged by vehicle traffic, freezing and thawing, rainwater, etc., and their service performance gradually declines. Developing countries often experience harsh natural conditions and traffic conditions, resulting in early pavement damage and impaired ability to carry traffic. Examples in the case of asphalt pavement include surface cracking, irregularities due to slippage and peeling, alligator cracking arising from interconnected cracking, and potholes in the pavement surface. Typical road pavement includes asphalt pavement and concrete pavement. But in developing countries, with the need for rapid road development and numerous opportunities for widening existing roads, asphalt paving, which is faster to construct, is preferred. Among asphalt pavement damage to roads in tropical countries, flow rutting is a particular issue. Rutting refers to groove-shaped deformation of the road surface caused by traffic load. It is characterized by ruts along the traveling position of the wheel and outward swellings. It is a problem that appears sometimes as early as a few months after completion of the asphalt paving. The asphalt mixture that makes up the surface course and binder course is produced by mixing asphalt and filler with aggregate, such as crushed stone and sand. There are times, however, when traveling vehicle load causes the asphalt mixture laid on the road to deform like soft candy. This condition is known as flow rutting. Why does flow rutting occur? Determining distribution of aggregate gradation and asphalt type and content in the asphalt mixture is called the mix design. Sometimes, however, there are inappropriate mix designs or inadequate quality control at the asphalt mix manufacturing plant. For external factors, the most common causes are intense stress on the road surface due to heavy traffic and softening of the asphalt caused by high temperatures. For tropical countries, solving this flow rutting problem is a matter of urgency in order to make vehicle travel safe and comfortable.
アフリカ諸国をはじめ、多くの地域では今世紀に入って経済成長が著しく、大型トレーラーの急速な普及など交通荷重の急増が見られます。JICAの道路事業においても過去の 舗装損傷事例が報告されていますけれども、その中でもアフリカ地域における流動わだち漏れが顕著です。アフリカ諸国では流動わだち漏れへの対応に頭を悩ませているのが実情です。JICA としてもこのような状況を踏まえ、流動わだち漏れを重要な課題と位置づけまして、その対策を検討してまいりました。流動わだち漏れはひび割れのような舗装構造の破壊ではありません。その原因はアスファルトの混合物層の流動として捉えるのが一般的です。アスファルト混合物は温度が上がるにつれて柔らかくなり、変形しやすくなる。そこに大型車が通れば、車輪直下の混合物は流動し、わだち漏れが発生することになります。道路舗装ハンドブックの改訂版では、流動わだち漏れに関係のある動的安定度、すなわち DS 値に着目いたしまして、調査段階において施工時の目標となる DS 値を事業地域の気温や交通量などに基づき設定します。そして施工準備段階や施工段階でその目標とする DS 値を確保するために材料の選定、配合試験を行います。目標となる DS 値が1500を超える場合はストレートアスファルトでは限界がありますので、回質アスファルトを使用するなどの検討が必要になります。
Main roads in many developing countries experience natural environment conditions with unique weather and soil conditions, including temperature and rainfall, and traffic conditions such as increases in large vehicles and traffic volume. In some construction circumstances also, it is sometimes difficult to secure materials of consistent quality. In terms of design, the design standards adopted in the partner country are not always adequate from the perspective of preventing flow rutting. In addition, taking percentage of air voids, for example, even if a test exists with the same name, the definition may vary. Or, like drainage design, measures differ by country. Unexpected pavement faults and damage could result if the partner country's natural and social environments, design philosophy and operation methods are not adequately understood. To address these issues, it is desirable to conduct preparatory surveys for design standard features and differences in design and construction conditions in developing countries, and take appropriate measures at the design and construction phase. To this end, JICA has implemented comprehensive surveys and analysis of the types and causes of pavement damage in various developing countries, and has conducted basic research to improve rut resistance. JICA compiled the information and knowledge gained from these projects, and in February 2020, made proposals in the form of the Road Pavement Handbook for JICA Grant Aid projects. Among preparatory surveys for grant aid projects, those relating to road pavement are generally implemented in the following sequence: data collection of similar projects, and pavement design conditions survey, road surface design, structural design, and design review. In a pavement design conditions survey, local conditions, related pavement materials, and information from similar projects are collected, and the necessary investigation for pavement design is conducted, enabling a design that considers factors such as soil conditions. Survey items include a review of natural conditions, including geological and weather surveys, traffic conditions, and a construction-related survey. Apart from calculating the California Bearing Ratio, CBR, of the subgrade, the geological survey checks groundwater level, the existence of problem soils such as dispersive soil and expansive soil, and soft ground. The weather survey covers rainfall and temperatures in the project area. In regions with particularly high temperatures where the road surface becomes very hot, caution is required as those areas are prone to rutting. The traffic condition survey covers traffic volume, travel speed and axle load on the target roads, and estimates future traffic volume. Caution is required in developing countries where there is a particular tendency towards a drastic increase in the volume of large vehicles. The construction-related survey covers a site survey and local contractor interviews regarding paving materials, such as aggregate, that are locally accessible and available asphalt plants.
現地では日本と異なる法制度、技術基準により建設事業を行っておりまして、気温や交通量などの自然条件や交通条件も日本とは異なっています。また、日本にはない分散制度や膨張制度などが存在する地域があります。このことを踏まえれば、各プロジェクトの事例を収集し、舗装設計条件の調査をしていくことは、今後の JICA の事業を効率的、効果的に進めていくために重要でございます。
In the design of asphalt pavements for tropical countries, flow rutting is the main issue for road surface damage, and poor drainage is the main issue for structural damage. Road surface damage can be prevented by clarifying the required performance for the road surface at the road surface design stage, selecting asphalt and making decisions on surface course materials, including the necessity for modifiers, aggregate quality and gradation to satisfy this performance, and then designing and manufacturing the mix. The term road surface design refers to one of the unique features of pavement design in Japan. Structural damage first requires appropriate implementation of design condition surveys, including CBR tests and axle load surveys. Then, based on the traffic load, subgrade conditions, climate conditions, and material conditions obtained from these surveys, structural calculations are made to satisfy the specified strength throughout the specified design period, and a structural design that appropriately determines material and thickness for each pavement course is conducted. Even with proper design, repeated heavy traffic over a long period can cause fatigue failure in the pavement. Groundwater and inappropriate maintenance also allow intrusion of water into the pavement from pavement cracks or gutters. This results in loss of bearing capacity of the base course and subgrade, leading to damage. Within pavement design, it is road surface design that is most important to counter flow rutting. At JICA, we recommend using dynamic stability, target DS value, which is commonly used in Japan as one of the standard performance indicators against flow rutting of pavement. This is a method to obtain target estimated DS values based on actual results in Japan using the target amount of rutting and service period, and external factors such as heavy vehicle traffic, wheel load, driving speed, road surface temperature, etc., and to refer to them when designing the asphalt mix. When calculating this estimated DS value, find the travel speed correction coefficient from the travel speed of the project road and the temperature correction coefficient from the road surface temperature. As the graph indicates, when travel speed is 10 km per hour or less, and the road surface temperature exceeds 50 to 60 degrees Celsius, the coefficient increases rapidly and the estimated DS value also increases. In addition to the estimated DS value calculated in this way, the target DS value is determined based on a comprehensive judgment that takes into account information on the pavement of surrounding roads and special circumstances such as heavy vehicles entering and exiting from roadsides and local traffic congestion. Based on this, when the required performance, target DS value, is set at no less than 1500 passes per millimeter, during design, the use of modified asphalt is considered. Materials used in paving must be of a specified quality for the base and sub-base course, surface and binder courses based on the road surface and structural design. For that purpose, at the construction preparation stage, the construction contractor will implement material tests, mix design, and construction management. In order to ensure that the asphalt mixture exhibits the performance required in the road surface design, such as flow resistance, we need to pay attention to detail in the mix design. The mix design uses specified quality materials and determines aggregate and filler selection, grain size distribution, asphalt type and asphalt content to ensure achievement of the target DS values specified in the road surface design. Japan's mix design method is conducted as a combination of the Marshall stability test and wheel tracking test. The wheel tracking test is a test that checks dynamic stability. The test uses a small, hard rubber wheel loaded onto an asphalt mixture test specimen that repeatedly travels back and forth at a specified temperature and speed to calculate the number of wheel passes required for a 1 mm increase in rutting in the specimen. Under Japan's test, it is difficult to achieve the target DS value of 1500 passes per millimeter or more with straight asphalt. However, using modifiers increases paving costs, so initially the requirement is to use given materials and increase the DS value as high as possible without compromising the workability and durability of a mixture. In many road projects outside of Japan, pavement work costs account for over half the project costs, so economic paving is a major concern for the contractor. The flow resistance and durability of an asphalt mixture varies considerably depending on grain size distribution in the mix. Coarse aggregate does not pass through a 2.36 mm sieve, and fine aggregate passes through a 2.36 mm sieve, but not a 75 micrometer sieve. Too much fine aggregate and filler produces a mix that is lacking in flow resistance. As this diagram shows, in a mix design that prioritizes flow resistance, the coarse aggregate interlocks firmly together, enabling a skeleton to be formed. If the coarse aggregates are interlocked to form a skeleton, and the right amount of filler and asphalt is interposed between them to make the bond strong, the mixture will be highly resistant to flow. Asphalt content has a particularly large impact on flow resistance and must not be too high. Generally, the optimal asphalt content for the Marshall stability test in Japan is likely to cause flow rutting in the tropical country's environment. Some decrease of asphalt content should be considered. However, care must be taken because too little asphalt sometimes causes construction problems such as fine cracks and a tendency for loss of durability. It is difficult to make a direct judgment as to whether the coarse aggregates have formed a skeleton, so the volume of voids contained in the compacted mixture should be kept above standard using the Marshall stability test method or a machine called a gyratory compactor. Aggregate shape is also important, particularly for fine aggregate. As natural sand is close to a spherical shape, its use is undesirable in terms of good flow resistance, so artificial sand should be mixed in. In addition, it is very useful to use low penetration asphalt, such as 40 to 60 penetration. In this way, even without using expensive modifiers, to a certain extent, the DS value can be increased by just taking care with aggregate mix and asphalt content. When wheel tracking test results do not yield the target DS value and modified asphalt is used, care needs to be taken with the type of modified asphalt and asphalt plant type. There are two types of modified asphalt: premix and plant mix. The premix type is made by an asphalt manufacturer, where the modifier is mixed in the straight asphalt in advance at the plant. Conversely, for the plant mix type, when the asphalt mix is manufactured at the asphalt plant, the modifier is added directly to a mixer, mixed, then used. When using modified asphalt, there are countries where the premix type is not available in the market. Furthermore, when considering the plant mix type, the modified asphalt manufacturing method varies depending on the type of asphalt plant. There are two types of asphalt plants: batch type and continuous type. In Japan, batch type asphalt plants are commonly used, where each material is weighed one batch at a time in a weighing tank, and then mixed in a mixer. On the other hand, in many African countries and Australia, the continuous type is commonly used, where each material is continuously supplied at a specified flow rate. Manufacturing modified asphalt using the continuous type requires equipment modifications. Based on these considerations, when modified asphalt is expected to be used, information needs to be collected in advance, including the asphalt procurement situation at the project site and the available plant type. Next, a batch trial is conducted based on the mix design, where an actual asphalt plant is used for a trial mix of materials. For the batch trial, the asphalt mixture is produced while adjusting the cold hopper flow rate and hot bin aggregate proportion to ensure they are the same as the mix design. As with the mix design, the required performance tests such as Marshall stability test and wheel tracking test are conducted to confirm that the required performance is assured. As a result, the mix design may be amended if required with the supervisor's approval, and on-site mixing parameters such as plant mix proportion, asphalt content, mixing time and target temperature, as well as management targets at the asphalt plant are set to ensure a proper production system for the product. In conjunction, trial construction is also implemented to confirm the workability and to determine the construction method and conditions. The asphalt mixture is manufactured by mixing sprayed heated asphalt with heated crushed stone, sand, filler, etc. Material tests are conducted on the materials used in the asphalt mix, and then checked to ensure they satisfy the specifications. In developing countries, stone crushing plant equipment is often inadequate, leading to problems with aggregate shape or disparities in gradation and properties, depending on the quarry and the crushing plant. Careful quality control is needed using tools such as material tests. When the paving works commence, quality control is important in asphalt mixture production. In particular, deviation from the specified particle size range of a specified gradation for the asphalt mix significantly impacts asphalt mix properties. This is an example of an extraction test conducted after collecting a core sample of the asphalt layer on a road. In sections where serious defects are observed, the test results show that nearly all gradations deviate greatly from the standard. This is likely due to too many fine fractions and insufficient interlocking of the coarse aggregate. In sections maintaining a favorable state, gradation is largely within range. As this example shows, an increase in fine fractions causes a major reduction in flow resistance. The out-of-scope grain size distribution in this example is thought to be caused by inappropriate control at the asphalt plant. This demonstrates that, even with appropriate mix design, inadequate materials and plant management will result in the manufacture of low-quality asphalt mix. To address these issues, under grant aid projects, specialists with the appropriate plant management experience and skills are assigned, and the contractor takes responsibility for managing the asphalt plant. Asphalt plant management can be broadly divided into periodic management and routine management. Periodic management uses basic tests and inspections to assure stable quality in the plant, and conducts these during plant construction before works commence, during batch trials, and when production is stopped during work periods. Control items include inspection of asphalt plant equipment, such as measuring devices, cold hoppers, thermometers, and asphalt discharge equipment. Items outside of routine management are also conducted, such as checking properties of aggregate gradation and asphalt property tests. In routine management, based on data obtained during periodic management, we confirm that errors are within the acceptable range and that there are no changes or abnormalities in the asphalt plant production processes, materials, or produced mixture. Routine process checks include inspection of equipment and operation control points prescribed in the quality control standards through visual inspection before and during work. Control items including sieving tests of hot bin aggregate, moisture content tests, extraction tests to investigate mix gradation and asphalt content, and temperature measurement of the produced mix. Daily performance of these tests reveals fluctuations in the produced mix. For example, it enables detection of clogged or broken screens used for aggregate sieving. Please refer to the Road Pavement Handbook for JICA Grant Aid Projects, which details items to note in relation to plant management. Pavement works defects under grant aid projects are mainly caused by use of unsuitable materials, mix design that does not reflect natural conditions or traffic conditions, and inappropriate asphalt plant management. These factors demonstrate the importance of creating an organization capable of technical and quality control of paving and assignment of professional pavement engineers. Apart from these, it is vital to take note of aspects that have a major impact on quality. These include measuring mix temperature at the paving site, compaction management, and not paving during rainfall, etc. However, countermeasures for these have subsequently been promoted on site. JICA has compiled findings on these topics and produced a road pavement handbook that reflects these issues. We anticipate that by referring to this handbook, and in conjunction with new technological developments, such problems can be avoided in the future. Under JICA grant aid projects, the consultant acts as an agent for the implementing organization and oversees whether the contractor is constructing according to the contract, work specifications, and design drawings. The consultant also ensures that appropriate quality and works timelines are met through construction management aimed at the contractor creating effective roads that meet specified quality standards. In recent years, there have been further efforts to improve quality and enhance construction supervision and management through the introduction of joint meetings called Works Quality Control Meetings, attended by the client, JICA, the consultant, and contractor.
舗装の設計が重要なことは言うまでもありませんけれども、その設計通りの工事目的物ができなければ意味がありません。そういう意味で施工段階の管理は重要です。コンサルタントと施工業者が連携して品質管理ができる体制を作り、材料選定や調達、配合設計や試験を適切に行う必要があります。舗装の施工にあたっては、締め固めや温度管理などに留意せねばなりません。また、アスファルト舗装の破損は、プラント管理の不備に起因することが多いので、プラント管理の専門技術者を配置することが大切です。
In March 2018, JICA signed a grant agreement with Tanzania for grant aid for the project for widening of new Bagamoyo Road, Phase 2. Countermeasures to prevent flow rutting in this project included local collection of asphalt pavement materials to be used on site and wheel tracking tests in Japan, which enabled understanding of actual material quality and investigation of test methods. Weather conditions in the project area included daytime temperatures in excess of 30 degrees Celsius, with no decrease in temperature at night. These are harsh conditions for asphalt, so flow resistance was increased by using a polymer modifier. In July 2019, JICA signed a grant agreement with Guinea for grant aid for the project for reconstruction of the Sumba Bridge on the National Route No. 3. As Guinea did not have standards to counter flow rutting, an investigation was conducted on flow resistance countermeasures under Japan's road pavement technical guidelines. Due to the high volume of heavy vehicle traffic on the Sumba Bridge, a modified asphalt was used for the approach road sections and bridge surface pavements.
JICA では様々な無償資金協力事業を行い、これまでに培ってきた経験と知識を生かして事業に取り組んでいるところでございます。日本のコンサルタントや施工会社は高い技術力を有していますけれども、途上国の条件や環境には必ずしも慣れていないところから、破損などのトラブルも経験してきました。日本と各国の技術者が経験や知識を共有し、舗装の課題に挑戦していくことが大切だと考えています。
Roads are a particularly important part of social infrastructure, and as such, they will continue to be qualitatively and quantitatively improved. Road pavement could be described as the face of road infrastructure, and it plays a vital part in road quality felt by users. It is also responsible for the final finish of road projects. JICA will continue to contribute to high-quality road development in various countries by further preventing damage to road pavement and improving its quality, and in particular by analyzing data and collecting findings on flow rutting countermeasures. We will therefore proactively engage in information sharing and transmission with associated parties and organizations.